Welcome back, everybody. Hopefully the horizontally launched problems worked okay for you guys. What we're going to do now is we're going to start out talking about upwardly launched projectiles. There's very little new information in this. Again, it's just practicing what we know, doing it over and over again until you start to see that all the problems are the same. I can't say it any more plainly than this. If you're doing the practice problems, you might be okay. You'll probably be okay. If you're not doing the practice problems, you're probably going to get confused. So do the practice problems. Let's go. Now, this lab that it's talking about here, clearly we have not done this yet. We're going to do this when I get back. Also, this quiz, originally we had planned on doing it today. I decided that we should wait until next time. So we will have this quiz next time I see you on Friday. Yeah, Friday for you guys. So this quiz will be on Friday for you. We're going to watch some video clips. Sadly, I can't link directly from this clip here to the clip I want you to see, but the substitute should have a copy of the PowerPoint, and in the PowerPoint there is an active link to this video. It's an article you're going to read, take some notes, and we're not going to get to it today, I don't think, but concept check is a possibility. In fact, I will guarantee we won't get to this today. We'll just do this when I come back. So right now, what we should do is have the substitute, sir or madam, if you wouldn't mind turning off this video or pausing it for now, pulling up the copy of these notes that I sent you with the sub-plan, and letting the kids watch this video and then this video right here. They should have a reading sample they picked up when they came in on this same subject, but it's supplementary to these. This is different information in the videos, and they should watch these before we go any further. Now that you have watched the videos about Ken Block, the stunt driver, I want you to silently read the article about Ken Block that you picked up when you came in. Then answer questions 37 through 46 on your notes packet. We'll pause the video for a while. After the sub determines that everybody is at about that location, you can press play again. Okay, so here's the preview for the concept check that we're going to be doing at the end of this unit. It will not be today, it will be next time. 4 questions. A frog is thrown upwards with an initial vertical velocity of 8 meters a second and a horizontal velocity of 10 meters a second. What is the horizontal velocity 1 second after it's launched? Keywords there being horizontal, 1 second. And then down below, based on the same situation, what is the vertical velocity of the frog at the top of its path? Neither of these are math problems. We should be able to solve this, either some of you can now, but we should be able to solve this based on facts about the path of projectiles that you learn in this lecture. Number 3, a bunny is fired from a cannon with an initial velocity, or initial vertical velocity, of 110 meters per second and a horizontal velocity of 80. What is the maximum height of the bunny? This definitely is a math problem. It's a WTF style problem. And down below, what happens to the vertical, keyword vertical, y-axis, the vertical component of the bunny's velocity as it rises? Remember, we're not solving these problems now. I'm just showing you what the problems we're going to have on the concept check will be like. So, how far below an initial straight line path will a projectile fall in 1 second? An initial straight line path is a a horizontal path like this. So if a projectile starts out, here's a horizontal path, pretend that line is straight horizontal for me, please, and you throw the projectile, it's not going to continue going straight. Gravity exists, and it's going to start to arc downwards as soon as you let go of it. We want to know at 1 second, how far will that projectile have fallen? We can know this without knowing anything else, because what we're looking for here is y, And we know that the initial vertical velocity of anything thrown horizontally is 0. So we know the initial value. We know time is 1 second. And we know acceleration is negative 9.81 meters per second squared. So you should see that this is y equals VIT. Only we're going to disregard that because VI is 0 because we're dropping it horizontally or throwing it horizontally. Y equals VIT, which cancels out, plus 1/2 AT squared. Distance followed, gravity, negative 9.81, and this value right here is 1. And if you plug in all these numbers, you get about 4.9. So in 1 second, an object will fall about 4.9 meters. Now that's if we throw it horizontally at the beginning. Does our answer depend on the angle of launch? In other words, whether it goes straight, whether it goes an angle up or angle down or straight across, or the initial speed of the projectile? Which one of those two matters? Or both of them, or neither one. Pause here or take a second and ask your neighbors. Make a prediction. Does our answer depend on this or this? Well, the answer actually depends mostly on angle of launch. It can depend on both of them, depending on how we look at it. Angle of launch is the most important thing, because if we show upwards instead of straight across, then it's going to travel upwards before it falls downwards. But initial speed is also important. Now, if it's a purely horizontal launch, initial speed doesn't matter, because our initial speed will all be in the x direction, so it won't affect our y, our falling of the object. But if there's any angle to it at all as it comes out of the person's hand or out of the gun or whatever our scenario says, the velocity does matter. That initial speed will have an effect at that point. It's only when it's horizontal that the initial speed is 0. So here's an example of a projectile fired up. Here's what we call the gravity-free path. If there were no gravity, it would just keep going in the exact same direction forever and ever and ever, because we ignore air resistance. But there is gravity, and when we fire, it moves, but it falls each second down along this path. We call this a parabolic trajectory. Technically, any projectile besides one that's shot straight up or dropped straight down, any projectile has a parabolic, there's that word, path. Now in this case we've got half of a parabola, that shape from math class. If you launch it up from the ground you could have a whole parabola, but it's a general term we use to describe this slowly arcing curve. If you look, the x-coordinates doesn't change for each second that goes by, but the y-coordinates definitely do as it falls. So we have to separate the initial velocity as we leave the cannon into an x and y velocity in this case. X velocity is going to be constant because there is no, x is like this, because there is no acceleration on the x-axis. The y velocity will be affected by gravity. You already know how to do that. We break things into the x and y t-chart just like with our horizontally launched projectiles. Now, just like in the last test where we talked about the difference between things being dropped and things being launched upwards and falling back down with hang time, you have to be careful when you're calculating time in the air for an object. Since in this case, this object is projected upwards and then falls on the other side, half of the time it's in the air it spends going up to its peak, and half of the time it's in the air it spends falling down from its peak. So if you're trying to find how high something is, where the Vy equals 0, you're going to use time up or time down, not both. They'll be equal to each other. Because to get to the maximum peak, you'll need half of the time. You only have to go up or fall down. However, if you're finding the range is from here to here on x. It's going up and coming down again. It's still in the air the whole time. So to find range, you have to use total hang time, up plus down. Or in other words, you find your time, and then you double it and use that time to find how far it travels in the x direction. Just a reminder, Vx does not change. There's no acceleration in the x direction. And the Vi going up is going to equal the Vf coming back down. Whatever this value is, it will be the same as, where is it on here? This value right here. The overall vector right here, Vi, let's say it's 10 meters a second. And it's made of a combination of our initial y velocity, initial x velocity. These come together using the Pythagorean theorem, and we'll pretend the answer is 10. If this is 10, then at the end, this will be 10. Not the y, not the x, but the combination of the two. The resultant, the hypotenuse, will still be 10. Whatever your velocity is going up, that's also your velocity coming back down on the other side. As we see in this summary right here, whether you're going up or coming down, you got the same acceleration. You got one of your v's being 0, Vf if you're going up, and Vy if you're coming down. And so, it's going to be the same y. Just different signs. Positive if you're going up, negative if you're coming down. Now there's an animation here. I will show you this animation when we get back. We'll talk about it. Same with this. There's a movie that goes with this. I'll show you when we get back. Here's the challenge. I'm not going to tell you the answer today. I want you to make a prediction and write it down. A zookeeper has a rubber band gun to shoot food to a monkey who's too shy to come down from the trees. We've had enough animal cruelty in the concept check today, so we're being nice now. If the monkey isn't moving, should the zookeeper aim at the monkey, below the monkey, or above the monkey? Not going to tell you. Make a prediction. Remember, this is if the monkey's holding onto the tree and does not move. What about if the monkey lets go of the branch and does move? At the very second that the zookeeper shoots that banana, the monkey lets go and drops. In that scenario, should the zookeeper aim at the monkey, above the monkey, or below the monkey to get the monkey to catch the food in midair? Pause it here if you need to and make a prediction. We'll talk about the answer when I come back. So just some general things. Pretty much all we have to do now is practice these problems with some general things to keep in mind. Which of these angles that you see here, these different thetas, is going to provide us with the longest range for this soccer ball? 45, right? We follow that line, it goes farther than any of the others. That's a general fact. 45-degree angles is the very best launch angle you can have to get the longest range from something. If we think about it, both the vertical velocity and the horizontal velocity affect how far a projectile is going to go. Vertical velocity puts us up in the air, which gives us more hang time, which means we're in the air for longer, so we'll go farther. Horizontal velocity means we move faster, so while we're in there, we'll cover more ground. 45 degrees is the perfect mix of getting as much lift as possible from our initial VIY and as much range as possible from our initial VIX. So 45 degrees will always give you the longest range for a projectile. Some problems right here. A gun is fired upward. The bullet's vertical, keyword vertical, initial component of velocity is 100 meters per second. And its initial horizontal component of velocity is 50 meters per second. So in other words, we've got a bullet that's being fired like this. Let's see here, up at this angle. The vertical component right there is 100. The horizontal component right here is 50. If the bullet spends 20 seconds in the air, what is the bullet's range? Now range, that word right there, that's how far it travels on the x-axis. So which of these two numbers do we care about in this case? Hopefully you guys guessed this one. If range is what we're talking about, then the x velocity is what's important. As long as we have time, and we do have time right here. The only x equation, as we know, is v equals x over t. In this scenario, v is 50. X we don't know, we're trying to find that one. And t is 20. 20 seconds spent in the air. That 20 goes right there. So in this case, to find x, it's 50 times 20, or 1,000. The bullet travels 1,000 meters, because we multiply by 20 to cancel this out. Multiply by 20 over here. 20 times 50 is 1,000. Next, the gun's fired upward like before. The initial vertical component of the velocity is 100 meters a second, and its initial horizontal component of velocity is 50 meters a second. So the exact same thing. Here's the bullet, here's our y component, 100, here's our x component, 50. Now we want to know the bullet's maximum height. Maximum height is what we're trying to find. So which of these two do we care about, 100 or 50? Which one matters? Hopefully you guessed this one, the 100, because height is a y-axis style problem. We have to do a little bit more work here. It's a kinematic equation, but we're trying to find height, so y is my unknown. I know vi equals 100. We found that right there. I know a equals negative 9.81. And I also know VF. The reason I know VF is we're going to the maximum height. The vertical component of velocity at maximum height is 0. That's where it reaches its peak. So we're going to use the equation VF squared equals VI squared plus 2AY. And I write y instead of x there because we're going up instead of down. We solve for y. I'm not going to go through the math right here. I think we all understand how to use the problems by now. The important part is reading the setup that we have and realizing how that relates to the variables that we're going to list for this problem. There's the concept check. We're not going to do it right now. In fact, I doubt you've even gotten this far. If you have, that just means you're even better than I thought you were. Concept check will be next time. For the rest of class, work on your homework packet. It's not due when I see you again, but it will be due very soon, and I want everyone to be able to turn this in this time. Good luck!